When an enterprise suffers a catastrophic data breach, the failure rarely starts at the point of impact. The pressure simply finds the structural limit. Enterprise security typically begins with a high-density technical stack, firewalls, IDS, and IPS systems designed to filter malicious traffic. The operational limit of these tools is defined by the human organizational structure responsible for their deployment and monitoring. Cybersecurity roles form an interdependent system. Every analyst, engineer, and responder functions as a node in a living computing network. Miswiring this human network renders the most advanced software inert, while threats move laterally through the system. Mapping human roles through mathematical models reveals exactly how enterprise structure dictates risk management. This requires translating abstract job titles into computable mathematical variables. Organizational efficiency is a rigid systems engineering problem. The goal is to determine which enterprise structure minimizes response time during a critical cyber incident. Optimizing a cybersecurity team is a solvable equation. This grid represents the enterprise workspace. The Chief Information Security Officer acts as the core strategy node. We add the security engineer to design defenses and the analyst to monitor data streams. The set completes with the compliance officer and the incident responder. The analyst handles the highest data volume, detecting anomalies within millions of logs. The responder performs highly specialized work, digital forensics, and system recovery after compromise. These roles are connected by a workflow vector. The path flows from detection to analysis, then response and recovery. The enterprise functions as a strict pipeline, where the output of one node is the required input for the next. The challenge is distributing a massive volume of cyber threats across this finite pipeline. Sigma notation expresses this workload. Total work is the summation of all tasks distributed across the n roles in the team. Mapping tasks to the equation shows an analyst handling 10 monitoring tasks, while the engineer manages 7, and the responder handles 5 critical incidents. This distribution mirrors load balancing in computing, where traffic must be routed across hardware to prevent systemic crashes. An unbalanced summation creates a bottleneck at the analyst node, where threat data accumulates faster than it can be processed. When the bottleneck starves the downstream incident responder of information, the entire pipeline fails. Poor mathematical task allocation creates system vulnerabilities and increases response times during an attack. If the analyst is the bottleneck, the common response is to increase headcount by adding more analysts. However, scaling headcount introduces a new variable: communication overhead. Graph theory provides a model to calculate the communication links within this network topology. In our 5-node team, there are exactly 10 possible communication links between individual members. Adding just 2 more people to resolve the workload bottleneck spikes the network to 21 discrete connections. In a network topology, communication complexity grows quadratically as the number of roles increases. During a critical cyber incident, this dense web of connections causes delays and increases the risk of miscommunication. Adding personnel to solve a workload bottleneck degrades the team's speed unless the organizational structure is re-architected. Controlling this quadratic explosion requires a structured organizational intervention. In a centralized structure, the web reorganizes into a hub-and-spoke topology. Every decision routes through the CISO authority. While providing high control, the central hub becomes a primary bottleneck that slows response times. A decentralized structure allows departments to manage security independently. This enables fast local action, but the lack of consistency across the enterprise creates high systemic risk. The modern hybrid structure arranges nodes into local clusters, connected back to central governance. The hybrid structure balances the equation by combining central oversight with local flexibility. By pruning unnecessary communication edges, the hybrid topology solves the quadratic bottleneck. Maintaining an optimal hybrid structure requires regulating the remaining communication links through interfaces. Technical interfaces, like CM dashboards, filter data noise, while human interfaces define reporting lines. Process interfaces establish standardized workflows that move information from input to processing, then to decision and action. These factors define system efficiency, the useful output divided by the total communication overhead. Interfaces lower the denominator. By reducing overhead, they drive the overall efficiency of the enterprise upward. Proper workload summation maximizes output, while graph theory topology and strict interfaces minimize the overhead. Higher quality tools increase the capability of an individual node, but they do not solve the networking problem. While individual tools provide capability, the overall security posture is a function of how well the human network synchronizes that technical power. Achieving an optimal security posture requires engineering the human enterprise with the same precision used to build software. Organizational structure dictates risk management. Map the math, control the communication, and secure the enterprise.